Hello again, Justin Miller here, Oxford College Physics. This session we will be discussing spherical lenses. Ultimately, a lens is just some item that is composed out of some material that allows refraction to take place at both an entrance and an exit boundary. So we got ourselves a lens here, and we can have images formed by lenses. Commonly we see lenses in people's eyeglasses. That's a great place that we see magnifying glasses. Those are just all lenses. There's a lens in our eye as well, all sorts of good things going on. But really, we want to understand how images are formed regarding the lenses. So first off, when we're looking at spherical surfaces and images formed due to spherical surface interactions, we had a nice expression that we developed, n1 over p plus n2 over q is equal to n2 minus n1 divided by r. And that's a really nice expression there. What can be done is that expression can be used for both entrance and exit through a lens and put together to develop a nice expression. So I'm going to forego the algebra involved with that because it gets a little ugly and distractive. But nonetheless, we keep on going. It can be shown for a thin lens. Shown. One over p plus 1 over q is equal to 1 over f. That looks familiar, huh? It looks just the same things that we had regarding spherical mirrors. Well, there's some other things going on with this, however, because f's a little bit different with lenses. F itself is equal to n minus 1 times 1 over r1 minus 1 over r2 quantity with a negative 1. So really, this interior quantity is 1 over f. So in order to find the actual focal length, take the inverse of it. And that's it. So first off, let's show what the focal length really is a representation of. Similar to how we define the focal point with mirrors, we define it with respect to lenses as the location where parallel incoming light rays will either converge to a point of intersection or trace back to a point of a convergence. So you have to dim the lights here a little bit in order to do this. In order for you to see it, we'll just go ahead and do that really quick. Ooh, nice, nice. So here, I've got a nice little lens that has two spherical surfaces. Got nice parallel incoming light rays. I stick the lens there, and what I have, they're all forced to converge to a point right there. That would be the focal point. The focal length is measured the distance from the lens to that point there. That's the focal length. And generally for thin lenses, just take it to be the center of the lens. Well, we've also got another type of lens that does something similar. It redirects light rays, but in this particular case, it produces divergence. The focal length for this lens is defined as the length from the lens to where these light rays would trace back to a point of intersection, which looks like it would be back over here somewhere. But nonetheless, when we're looking at converging lenses or diverging lenses, we've got ourselves the essence of focal length itself. So that's one thing to start with. The focal length is determined by the radii of curvature of the two surfaces comprising the lens, as well as the index of refraction of the material comprising the lens. This one here represents the index of refraction of air. We're just going to take lenses in air. If you start putting lenses in water and submerging them, then you have to change this 1 to whatever the index of refraction of that surrounding material is. We're not going to do that, so we're just taking that to be 1 as the index of refraction of air. So let's just take a look at a certain type of lens here. We can take that has a surface number 1, and a surface number 2. That's great, that are kind of connected together. We can have this surface number 1, well, since it's spherical, and ultimately make some sort of sphere which has some center. That would be the center of curvature regarding surface number 1. And then we've got this other surface over here, surface number 2. It's spherical as well. Maybe it traces back around there. And we've got its center of curvature is over here, C2. So we've got these centers of curvature. Now when we're looking at the radii of a curvature, what we're really looking at is, what's this distance here, R2, the distance from surface 2 to the center of curvature. And what is this distance? R1, the distance from the surface number 1 to its center of curvature. Those are the R's in that expression there, where this lens has some material that has some index of refraction. So what we have to first note is there are rules for these R's. So what we need to define R's is, what are we going to call front side, what do we call back side? Light goes from the front side to the back side. That's how we decide the direction, or determine the orientation of the lens, front side versus back. So let's just call this side the front side, and call this side the back side. And say that we're considering light rays going that way, and doing so. And then what we have is that there is a specific sign convention regarding these radii of curvature that are dependent on front side versus back side. So what we have is R is considered to be positive on the back side, positive if C is on the back side, and negative if C is on the front side. So if we look specifically at focal length of some lens like this, we'd have, in this particular case, C1 is on the back side, so R1 would be positive. And then we have C2 is on the front side, which means that R2 would be a negative quantity. And then in terms of the sign of F, well, that would be gotten by looking at the overall sign of what comes out of this. So we would have some n minus 1, n is going to be greater than 1, so this quantity here is going to be plus. And then we have a 1 over R1 minus 1 over R2. R1 is going to be positive, and R2 is going to be negative. So what we end up getting is a 1 over plus minus 1 over minus, and then to the negative 1. This is, again, just putting in signs of things. So we have plus multiplied by whatever this turns out to be will give us the sign of F. And we have plus, minus, and minus. This has to be positive here. So we have positive value multiplied by a positive value. Take the inverse of it, it's still going to be positive, and we will get positive focal length. This characterizes what is known as a converging lens. So say what is called a converging lens. We say converging because of what it wants to do with parallel incoming light rays. A converging lens will take parallel incoming light rays and force them to a point of convergence, the focal point. And that corresponds specifically with a positive focal length. So a lens has a positive focal length, it is a converging lens. A lens has this particular shape, it will naturally be a converging lens, where we have one surface convex, the other surface concave. Convex, concave. Let's look at another one. Take another type of lens here, where we'll make it more like an hourglass shape. Look at its radii of curvature. Take this to be surface number 1, take this to be surface number 2. Take ourselves this here. Have some C1 and some R1. We can take this one here. I have some C2 and some R2. And what would we say? Well, we say that R1 is positive, R1 is negative. Here, R1 would be considered to be a negative value because it is on the front side, front, back. And R2 would be the positive one because it is on the back side. We already know the n-1 part is going to be positive, so it really comes down to what is 1 over R1 minus 1 over R2. We have 1 over R1 minus 1 over R2 goes to, again, with signs, goes 1 over a negative minus 1 over a positive. Well, we have minus, minus. Both numbers are going to be considered negative. Adding them together gives us something negative. This will give a negative focal length. This characterizes what is known as a diverging lens. What is called a diverging lens. You ever have a lens shaped like that? It is diverging. This is converging. You can have other sorts of incorporations of spherical surfaces and have crescent types of shapes. Then it depends on which radius of curvature is the largest versus the smallest according to the front side, back side. Not really worried so much about that, but that's it. That's how we understand the focal lengths, the naming convention for them, and the sign convention regarding the radii, I should say, of curvatures. Radii of curvatures. Yes. All right. So 1 over P plus 1 over Q is equal to 1 over F. That's super simple. We've already done it with mirrors. What we have to be careful of, once again, is sign conventions, however. Sign conventions for lenses are slightly different than sign conventions for mirrors. And it has to do with the transmission of light versus the reflection of light. So, we look at this. Sign conventions for lenses. P is positive. With the object on the front side, and negative the object on the back side. Which corresponds to what is known as a virtual object, where you need to have two interactions or more in order for that to take place. Q is positive on the backside and negative on the front side regarding usage. Then we still got M, lateral magnification, is defined as H prime over H, which in the case of lenses is equivalent to negative Q over P. So that's familiar with respect to lenses. So that's really it for the sign conventions. In terms of virtual objects, again, we'll deal with that a little bit later. Single interactions, there are no virtual objects. Objects are real, and it's just a way of treating compound systems. So one last thing that we want to look at before doing problems is sign conventions. Excuse me, it's ray diagrams, which is sign conventions. Ray diagrams regarding lenses. So just like with spherical mirrors, ray diagrams involve three primary rays, but slightly different in terms of the composition. We're looking at three primary rays. We'll have that the first ray goes parallel to the principal axis and refracts such that it is aligned with or goes through a focal point. Such that line width or goes through a focal point. Second ray goes through the intersection point of the lens and the principal axis, unchanged in its path. And we got ourselves a ray number 3, third ray. A little scared. Green doesn't come out super good with text. So go over with black here. Third ray goes through or is aligned with the other focal point. refracts parallel to the principal axis. So notice it says other focal point. All lenses have two of them, one on either side, equidistant for the lens. Equidistant from the lens, excuse me. Because flipping the lens around doesn't change anything about it, no matter what it looks like in terms of spherical lenses. So just a little demo of that, just to kind of see. I can take this little lens here, I can put it like this, get the focal point right there. What happens if I go ahead and just flip it around? Focal point's still just right there. It doesn't matter, ultimately. Even if the shape of this side and this side are different, it doesn't change. So here is a plano-convex, or excuse me, that's plano and plano-convex, depending on which way you hold it. One side's spherical, the other side's flat. There's the focal point. I turn it around and still get to this, the distance away from the center. This starts to not be a great lens to look at just because it's so thick. It exceeds the thin lens approximations. This one probably a little better. That's gotta be it. This one maybe is. No, that's just this. Anyways, that wasn't very helpful, but when we turn the lens around, it doesn't do anything. Changes the orientation of the surfaces, but it also switches their signs and ends up having no effect on the focal length. We define two focal points. So we'll draw out a nice little ray diagram regarding lenses and move on to some problems afterwards. So with lenses, we are assuming thin lenses, even though there is two singular refractions taking place, one at the entrance boundary and one at the exit boundary. If it's thin, we can just ultimately approximate that there's one overall refraction taking place, and then it makes things a lot easier for us. So when we draw out these diagrams for lenses, generally we'll just draw the lens like this. There's the lens, there's the principal axis. What do we have? We have focal points on either side of the lens that are the same distances away. We don't want to make one f1, one f2, it doesn't matter, they're both the same. So we've got these focal points, and then we go ahead and stick an object here. We say, okay, here's our object. Where's the image going to be produced? We take this first lens and say it goes parallel to the principal axis, and then either refracts and goes through a focal point or is aligned with a focal point. That comes down to one thing. What type of lens is this? Is this a converging lens or a diverging lens? If it is a converging lens, this first ray goes parallel and then is forced down through the focal point by the definition of convergence. If it is a diverging lens, this parallel ray goes like this and then it diverges, and that divergence is aligned with this focal point. So what is considered this to be a converging lens here? Messy. And we'll just look at these. So first ray, parallel to principal axis, reaches the lens and then undergoes its refraction. Ooh, there we go. Keeps on going. The second ray goes through the intersection point of the lens and the principal axis itself. So I'm just freehanding this out and get it done quick. Ultimately, something like that. Then the third ray goes through or is aligned with the other focal point. We haven't used this one yet. We've already used this one. So guess what? We've got to use that one. I'm going to switch this to a red color. Now we go through the focal point, and then it refracts parallel to the principal axis. There it goes. What do we get? They all physically intersect right here at the location of our image. We've got a P, we've got a Q, and we've got an F. And we will have 1 over P plus 1 over Q is equal to 1 over F, and the magnification is equivalent to negative Q over P. The sign of the magnification tells us whether it is inverted or upright. Negative magnification, inverted. Positive magnification, upright. Magnification absolute value greater than 1 gives us an enlarged image. Magnification with an absolute value less than 1 gives us a diminished image, size-wise. And it's pretty much that. So you just really got to be careful of making sure you utilize both focal points. And for converging lenses, not that bad, but for diverging lenses, it can be a little bit more tricky. But we'll look at those in a problem.